What's up, folks? So we're going to finish off the SDXL derivation today. Last time we stopped, we ended up at the general decomposition of the elbow loss, and now we're going to put in the parameters of our Gaussian, and we're going to use Gaussian PDFs and solve all the way down, simplify all the way till we get the L2 norm that you see in the SDXL paper. So let's get started. This should take me about 30 minutes to get through. So it should be an even split between, this should be the last video I make. So again, I'm just going to use my notes. I'm going to start just, using a pointer on my notes that are already created because I think it's a lot easier. I like how it flowed last time. I thought it was very clear. And you can pause the video if you don't understand or need to look at, you can download the notes yourself. You can pause the video at any point and look at the notes, look at the equations if you need to get a closer look, if I'm going too quickly, right? So I'll leave the pacing up to you. Okay, so when last we stopped, we had this final decomposition, right? This is the diffusion. This is the diffusion loss. And depending on how you parameterize, depending on your modeling assumptions for the noising schedule, you'll have different distributions with different parameters. But like I said before, I'm pretty sure that the large majority of the variance of the time schedules, the noise schedules that you can use will all simplify to a squared L2 norm. Don't take, I'm not 100% sure on that, but I've seen quite a few of them simplify to those values. So yeah, just know that the squared L2 norm is a very common simplification that you will arrive to. Okay, so we're on the last step of our derivation steps. So last video, I walked you through these four, and now we're just going to do the difference between the PDFs, the expected difference, and the expectation of the difference, and we're going to simplify that down. So, okay. So we're not going to consider any of the terms except for this one. The other terms you can just drop, we just dropped for simplification. That's just what the authors decided to do. It still satisfies the evidence lower bound. So if we're looking at this, so we remember in the first two parts, I think in the second part, in the second video, actually, we define, well, in the first video, we defined the forward process. In the second video, we define the posterior, the closed form of the posterior, right? We calculate this posterior and then we get the closed form solution, which allows us to get a closed form estimate of the denoising process, which is our model, right? So we have the parameters of these two Gaussians. If you're confused, then watch part one and part two. I think namely part two, but you need to watch part one to understand part two. So, okay. So this is the true posterior. And these are the parameters of the Gaussian. We have this mean that we've defined. I'm not writing it out here, but we do have the closed form solution of this mean. It's actually, I'll just show you really quickly. It's down here. We got that from the second video as well, both of these. It's both the same thing, except one, I'm predicting noise. I'm using the predicted noise vector from the model, and one I'm drawing from a standard normal. So I'm calling this mean M1 and this mean M2, and you can see that the variances are the same. So, right, so if you look at this, this is the product, sorry, this is the sum of the expectation of the KL divergences. I just realized. So I realized I needed to change the aspect ratio. Okay. Okay, right. So we're looking at the sum over time steps of the expectation of the KL divergence between the true posterior and the approximate, the predicted noise, the predicted posterior, which is your model's prediction. So what we're going to do is to calculate this KL divergence. Remember, the definition of KL divergence is the expectation under P of log P minus log Q, right? So we're just going to look at the log PDFs of P and Q. In this case, this is our P and this is, well, okay, we're going to look at the log PDF between the difference of the log PDFs between these two functions, between these two distributions, right? And because the covariance is the same, right? So really this KL divergence is just looking at the variance of these distributions is the same. So we can that's why this actually resolves to a squared L2 norm, is because the variance is the same. Otherwise the math would be a bit more complicated. So okay, this is the PDF of a multivariate Gaussian. And so we're going to call, so this is P. We're going to call P, so I'm color coding this. So the true posterior is going to be salmon colored. The mean of the true posterior is going to be salmon colored, and we're going to call it M1. And we're going to assign this distribution to P. And this we're going to call Q. I see that might be confusing because I'm already using P and Q. Okay, well, we're going to keep going. Green M2 is going to be Q. And then we're going to do log P minus log Q. Damn, I should have. I'm going to actually change this right here. We're going to call this R and S. Yeah, we're going to call that R and S. And we're going to call this R and S. Yeah, okay. So the log PDF of a multivariate Gaussian is this. So if we do log R minus log S using M1 and M2 and sigma, and the same sigmas because the variance is the same, right? If we take those two differences, that's what we get. We're just using M1 and M2 just because it's a little bit neater. We're going to do a bunch of algebra with these dummy variables, and then we can substitute back in the real values. So I'm just using, this is A, I'm calling this A and this B, just to make this shorthand notation. I'm just showing you that I'm pulling out this 1/2 right? So I have 1/2. Well, so, okay. So these values cancel, right? Because it's negative this plus this, right? So we can cancel those out, and then we pull out the 1/2, and then we're left with this minus this, okay? We can see M1, M1, M2, M2. FYI, this is called the Mahalanobis distance. It's actually a distance measurement. It's the squared L2 norm is a specific case of the Mahalanobis distance. So, okay. So now we take the expectation. Okay, so remember, this is an expectation, right? It's an expectation of, well, hold up, wait. KL divergence, sorry, yeah, KL divergence is an expectation of log R minus log S, right? So now that we have the difference simplified, right, we're going to do an expectation of these two Mahalanobis distances, and we can pull out the 1/2, right, because expectations are linear functions. And our P in this case is the distribution with M1, which is the true posterior, right? So, okay. Right, so now we're on a step where we're looking at the expectation under the true posterior of this Mahalanobis distance of the true posterior minus the Mahalanobis distance of the predicted posterior. So now we're going to use these identities, these properties here, and I'll call them out as they come up. Actually, we don't use this. So, okay, so now I'm going to distribute the expectation through. I'm just going to look at expectation of A first and then the expectation of B. So the expectation of A is this, right? By the properties of trace, the basically it's saying if this is a scalar, then the trace, basically a scalar is equal to the trace of a scalar, right? But that's not the important part. The important part is when you wrap it in trace, you get to reorder the terms inside of the trace. Okay, so right, I'm using this property and I'm saying that this is equal to the trace of this, and then I switch the order of this vector in the inverted covariance matrix, the inverted covariance matrix. And then I use this property, we use this property, which is the expectation of the trace is equal to the trace of the expectation if right. And so we use this property and we bring the expectation inside. And then so we bring the expectation trace of the expectation, or we bring it here. And because sigma is not dependent on x, right? Then we can pull the sigma out of that expectation. So we end up with this. And then right, and then this is equal to the covariance. The expectation of this times this is equal to the covariance. And so then we have the trace of sigma inverse times sigma, which is the identity, right? And so the trace of the identity, if it's in RD, is equal to or d by d, right? Which is summing up along the diagonals, and then we get d. So expectation under P of A is D. And so now we're going to look at the expectation of B, right? We're going to distribute it and look at expectation of B. And so, okay, now I put this in here. So we're going to do this, we're going to treat this one a little bit differently. So we're going to call R x minus m1, and then delta is m1 minus m2, okay? So now we're going to look at x minus m2, right? And then we're going to say x minus m2 is equal to this, which is R plus delta, right? Because the m1s are just going to cancel out, and that gives us x minus m2, okay? So x minus m2 is equal to R plus delta. So we're going to put R plus delta into these two, and we get this. Okay, now I bring the sigma inverse through, and I'm going to use these properties, these algebraic properties, these linear algebra properties, or vector math properties, to expand this and simplify, right? So now I do this times this, and I do this times this, I get this, okay? Now I just put these in colors so you can see that these are the two that I'm considering right now. I want to turn this into this. They're the same thing. This and this are the same. And I'm using this property right here, that this is equal to this. So this turns into this. Now they're the same, and I add them together. And, right, so now I have the expectation under P of this, right? That's what this is right now. So, and now you can see why we wanted to bring in M1 into there, because it's an expectation under P, and M1 is the mean of this distribution, right? So that's going to help us simplify things. So now I'm going to bring the expectation through here and here to look at those three cases individually. So the first case is this one. So the expectation of that, again, I use the properties of trace to bring this out, and then bring the expectation here, and then bring the sigma out and get this, right? This again, right, is the variance, is the covariance matrix, okay? So then this is the identity, and this is another D. So this is D. Now we look at the second term, the expectation of this term, and only R is the only variable here that depends on X, right? And this expectation is X under P, right? So we bring everything outside of it except for R. What is the value of R? R is X minus M1, right? If this distribution E is under, this is P. So P, I'm just using shorthand so I can fit all these things on one line. P is this distribution, right? That's what we're looking at the expectation of right now. So P is this, so the expectation. Now, the expectation under P of R, right? This distribution P, the parameters, the mean is M1, and this R is removing M1 from each X, right? So just like we would do if we were trying to turn a distribution into a standard normal, right? So this mean is going to be 0, right? So that zeroes out this whole thing. So the third expectation under P is none of these on the inside depend on X. So we move them all to the outside and we have 1. The expectation of 1 is 1. So now we're just left with these constants. So this turns to D, this is 0, and this, the third one, gives us these constants. So the expectation, so if this whole thing is Q, so the expectation under P of Q here is equal to this. Well, remember where delta is defined as M1 minus M2, right? So if we swap delta for M1 minus M2, we get this. And if sigma, right? Sigma is diagonal covariance, is a diagonal covariance matrix, right? So then that means that this is just the squared L2 norm of M1 minus M2, right? Because this is just 1 over sigma squared times I, right? And then we can bring the sigma squared out and leaves us I here. That's just this times this, which is the L2 norm by definition. So therefore, that's what these 3 dots mean. Going back to the very beginning where we were trying to figure out what what this expectation is, the KL divergence, right? It's this expectation of A minus B, where this is A, this is B. So therefore that, right, equals, so remember the first expectation under A, expectation of A under P is equal to D, and then expectation of B is equal to D plus this. So we're going to have D minus D plus this when we do the expectation of A minus B altogether, right? That gives us this. Those cancel, and then this cancels, and then this multiplies with this, and we're left with this, where it's the squared L2 norm of these 2 means. Okay, just like we showed in this tiny little image up here, because the variances are the same. So we know that the KL divergence is just going to be looking at the difference between these 2 means. We're proving that interesting. We proved that just now here, okay? So now we're just going to bring our parameters back into play. So we know that our variance is beta estimate, beta tilde, and we know that our means are mu post and mu sigma. We define that because we know the parameters of our distributions, right? We define that right here, right here, okay? So I'm still color coding them so you can refer back to them in their original places, right? So mu post, mu theta, all right? So we have a squared L2 norm, but of the difference between the mean of the true posterior minus the mean and the mean of the predicted posterior, the model's prediction. So, okay. So now we're gonna do one more step to bring it to the epsilon form you see in paper. So if you recall from from 2 videos ago in the reverse process, when we were deriving the reverse process, we use the sampling form of a Gaussian. So the parameters of our, right, so the parameters of our, so it's, the parameters of xt given x naught. It's our one-shot kernel. Right? And we just write it as the sampling form of the Gaussian, where epsilon is from a standard normal. Now, if we solve for x naught, I did this math in a previous video, but just to connect the dots here, if we solve for x naught, we get this. And then if we substitute epsilon with our model's prediction, we get x hat naught. Okay, that's our prediction for the image that we're trying to generate at time step t. Okay, so now we have x naught and x hat naught. So remember, I didn't write the equations for, so there are equations for mu there's an equation for mu that's based on x naught, and if we substitute in x naught hat, right, we'll get and if we substitute in this for x naught, we can parameterize mu in terms of epsilon. And then if we substitute in, for x naught, we swap it with the definition of x naught hat, right? Then we'll get the mean for the model's prediction, right? So we'll get these 2 equations. And then if we substitute, so if we're trying to get this in terms of epsilon, right? So now we're going to look at this difference, right? We just do some algebra. We We do this one minus this one. These x's will cancel. Then we can pull out this. We can pull out this, and we can pull out this and this. And we can, then it'll be this minus this, and we can pull out the betas, and we'll get this. Sorry, we'll pull out these beta, these scaling terms, and we'll get this. And then I'm just multiplying these two together, just combining them to make it neater, to make it all one weighting term, right? And now, if I surround, right? So now if I look at, if we just surround it, we just swap in, so this goes in here, right? Then if I want to pull this outside, of this squared L2 norm, we just have to square it, right? It becomes a quadratic term, right? So then that will remove this square root, and it'll add this here. Remove the square root, and it'll add this here. And then this is our weight, right? And now we have it in terms of epsilon, and this is our weight, which we can drop. In the paper, they drop this. It's a time step dependent weight that it can become a hyperparameter, but they drop this. So this is our final, so this is our final objective function. The difference between the amount of noise that you actually added using the forward kernel and the amount of noise that the model predicts that you added. You backpropagate on that loss, and that's how you train SDXL. So there you have it. Full SDXL derivation complete. You haven't seen this anywhere online. I haven't seen it anywhere online. You're welcome. I'm amazing. I know. Yeah, these things. I just love doing. I just love doing this kind of math. I just love doing this kind of math. I've always loved it. That's why I have a math degree. That's why I chose to do a math degree while I was majoring in computer science. I was like, I just love. It just feels so good to me. Just being able to just look at all this. Right? We started at the beginning with. Isn't this crazy? We started at the beginning with this. We said we want to find the parameters that maximize this log likelihood. And then we went through all this math, all this super clever stuff, and we ended up with this. Oh, right. Also, what happened to this? Right? Because we only considered this to end up with the squared L2 norm. What happens to this summation? This is the summation over time steps. So it's over your data. So we don't, right? We can just do like stochastic gradient descent by just considering data sample by sample, right? So we can just drop this term. It's, it's not necessary. Beautiful stuff. All right. Well, yeah, thanks for watching. So next, I think I'm going to code up DDPM, the actual noise scheduler, and use the diffusers library to open up the pipeline, code the pipeline manually, just use components that are already defined to code the pipeline manually. I can't train SDXL like I originally planned, which is kind of insane to even think that I wanted to do that, because that would probably take $1 million or something for me to actually, probably more. I'm probably, usually with machine learning, you're usually underestimating the amount of work it takes. So probably way more. But yeah, I'm going to use components to load a pipeline and then I'm going to load in my custom DDPM scheduler because I've basically coded all the other components for SDXL. And you know what? Next I'm going to do. I kind of did this out of order. I'm doing things as I'm inspired. Next, I'm gonna do a full breakdown of the SDXL model. I'm gonna take the architecture diagram and fully break it down because there's a lot to be discussed. I'm gonna do that, and then I will start coding. Maybe I'll start coding. I don't know. We'll see. Anyways, thanks for watching. Hope you learned something. The notes are uploaded. I highly encourage you to step through this yourself. If you want to be a researcher, if you want to be someone that really knows how to work with models, you got to learn how to do the math. I know you might be like, well, what is this algebra? Like, what does it matter if I can do algebra? It matters because when you start manipulating these, I didn't start to get a good handle on what it feels like to model a generative model until I started working through the math. Like when you start looking at these expectations and you're like, why is this expectation under this? And you're like, oh, it's under this because the forward process is something we define. So it's like, oh, it makes sense that the expectation would be under this forward process. It's literally our training data. It's hard to, for me, none of that stuff doesn't fully click and like live in your bones and live in your nervous system until you work through the math. My professors have always encouraged me to work through the math. You know what I mean? Maybe my computer science professors did it when I was an undergrad, but my math professors were always like, you want to understand optimization, work through the math. And I get it now. I get why they say that. So I strongly encourage you to download the notes and work through it yourself. Try to do the full derivation yourself. Anyways, I've been talking enough. Okay, thanks.